So yeah, just to recap our plan today, work through this 2024 MASA exam. So this is produced by the Maths Association of South Australia. Most of it's pretty good. There's a few things I'll point out later that I'm not heaps happy with, but most of it's pretty good. So yeah, let's get in here. So we've got part 3. So hopefully you're able to answer part 1 and 2. If not, I'm able to bring up a solution a little bit later. So we want to get these marks, right? Okay, again, I'm going to emphasize those points. There's what, 6, 7, 8, there's 11 easy marks here to get. You absolutely have to get them. Okay, so regarding this logarithmic function, the first thing I've done is expand that, okay? Because when we have ln of f of x and we're going to differentiate it, okay, it just goes to f dash of x on top of f of x. So we just have the derivative function at the top and the original function at the bottom. So here we have ln of f of x. Let's go straight to the derivative. So we have the derivative of the inside at the top. Alright, so just using the power rule. And then on top of the original function. And we can state it as it is here or in terms of roots. And again, being clear, y, dy on dx. Okay, now if I'm going too quick, please do stop me. X squared, take 5x plus 3 on top of x. Now we can't integrate that immediately, so we need to simplify it somehow. What I'm going to do is split that denominator so that we have, and again, I'll do most of these things over a series of steps just to really draw out the explanation. Okay, we can split the denominator. Now we can simplify most of these terms. X squared on x is x, 5x on x is 5, and 3 on x stays as 3 on x. And then we just integrate term by term. And then plus c. CD. Okay, question 2. Consider the function below. The graph of f of x is shown in figure 1. The graph intersects the x-axis at points A and C, where x equals A and x equals C respectively. Point B, where x equals B, is a local minimum, and point C, where x equals C, is a non-stationary inflection point. Point C, where x equals C, is a non-stationary inflection point. So it's a root and a non-stationary inflection point. All right, so that's a point of inflection. Good. And then point D is a point on the graph that is larger than C. Okay, so it just exists above C, and then this is a horizontal asymptote. Okay, complete the table below by indicating whether the function is, whether f of x, f dash of x, and f dash dash of x are positive, negative, or 0. Alright, so we've got x is b, c, or d, and then we have the function, we have the derivative function, and then we have the second derivative function. Okay, so with the positive, negative, or 0, all we're stating is, let's do the function first. Alright, so the function is the y value, right? We're always graphing y equals f of x. So at point A is the function, is the y value, positive, negative, or 0. It's going to be 0 at point we just have B, C, D. So at point B, it's negative. At point C, it's going to be 0. And at point D, the y value is positive. Okay. Then we have f dash of x, so we're talking about the derivative function, and the derivative function is just slope, right? So if we have negative slope, then the first derivative is negative. So at point B, the slope is 0, it's horizontal there, we have a stationary point there. At point C, we have positive slope, and at point D, we also have positive slope. And then the second derivative is where's it concave up, where's it concave down. So at point C, that's where the point of inflection occurs. The point of inflection occurs, that means it's going to be 0 on the second derivative. The point of inflection on the original function is a root on the second derivative. All right, and then at point D, the function is concave down. We can tell by the shape. So that's what that table is going to look like. All right. On the axes below, sketch a possible graph of f dash of x. All right, f dash of x. So we want to sketch it, and we've got these points here, A, B, C, and D. So what's going on? So what we should be able to see is we have a root. So f dash of x, we have a root when x is 0. On point B, there's a root there. At x is 0. That's the stationary point, right? So that's going to be a root. And before then, right, before point B, if we look at the original function, before point B, we have negative slope. So that means the slope function is below the x-axis before point B. All right, and we have a root there. All right, so that's the first part, so it's passing through point B here. Then at point C, we have a point of inflection, don't we? Now remember, points of inflection on f of x correspond with turning points on f dash of x. So we have a turning point at C, and it's going to be a local max, because it's approaching a maximum point there. And D is just an x value that's larger than C. And what we can see as well is that the slope's going down here. I'll make this argument as to why this is the case. It's going to go like this. We can see from looking at it, this is where the point of inflection occurs, point C. That's where the slope is steepest. Okay, that's got the largest slope, where the slope is maximized. The slope is less at point D, and as x increases, it is asymptotic, which means the slope approaches 0. Okay, so that's where we're getting the third mark. So we get a mark here for that maximum point, a mark here for the slope approaching 0, and identifying the correct location of the root. Point A, there's nothing special occurring about point A. The slope is negative at that point. Very good. Okay, turn the page. All right, a basketball player shoots a ball from a height of 1.5 metres above the ground. The vertical displacement of the ball can be represented by S of t function between 0 and 3, where time is measured in seconds. The graph of S of t is shown in figure 5 below. Calculate the gradient of the chord from t is 0 to t is 2. Very good. So our S of t function is 1 minus t squared plus 2.5 t plus 1.5. And we want to know the chord from s at time is 0 to time is 2. So to determine those y values exactly, we're just going to find s of 0, which is 1.5, and s of 2, can we see that directly from the graph? Is it 2.5 or should we not risk it? Let's chuck it in our calculator. Desmos. So t, negative t squared. Now we can evaluate it pretty easily, but I'm putting it in here as well to refer back to it in a moment. Plus 2.5 t plus 1.5. I need to use x. X squared plus 2.5x. And we want to know when x is 2. The y value is 2.5. Yep. So S of 2 is 2.5. And so what we're doing then is we're finding the slope of this chord here. We have this coordinate is when time is 0, the y value is 1.5, and when time is 2, the y value is 2.5. So we're just finding the slope of that chord. All right, slope, y2 take y1, on x2 take x1. So we'll have 2.5 take 1.5, on 2 take 0. All right, part 2, interpret your answer. All right, so slope of a chord is what we call average rate of change, right? The A bar. So the average rate of change from time is 0 to time is 2. And so it's the average rate of change of, what's the function? The displacement. It's the average rate of change of displacement. So on average, over that period, the displacement of the basketball is changing at half units per second, meters per second. Okay, show that S of t plus h simplifies to this. So B part 1. Okay. S of t plus h. So all you're doing there is putting t plus h into the S of h function. We'll perform a perfect square here. All right, just expansion. Okay, hence find S dash of t from first principles. Well, S dash of t is the limit as h approaches 0 of 1 on h of S of t. I'll just write it out as, S of t plus h, take S of t, rather than it being in terms of f of x. All right, so the one we're familiar with, 1 on h, f of x plus h, take f of x. Okay, here we have S of the displacement with regards to t plus h, take S of t. Okay, so keep going. We have S of t plus h is what we evaluated here. And so they've even given you, it's a show that, isn't it? Show that it expands to this. So even if you find that expansion tricky, it's provided for you. Take 2ht, take h squared plus 2.5t. All right. S of t plus h, take S of t. What's cancelling? We have minus t squared, take negative, so that's going to be plus t squared, that's going to cancel. So that term and that term will cancel. We have 2.5t and 2.5t, so 2.5t take away 2.5t, that term will cancel. And 1.5 take away 1.5, that term will cancel. So let's state what we've got left. then factorise h. Cancel, apply the limit, and we're left with minus 2t plus 2.5. Alright, so that's s dash of t. Run okay, going too slow, too fast. So s dash, next part then, find s dash of 2 from first principles. So here's the derivative function, and we know we're putting the number 2 into the derivative function. So that's going to be minus 4 plus 2.5 minus 1.5. Just a checkpoint here as well, like we know going through first principles, everything in this step should have h in it, so there's a checkpoint there. The other thing is we can perform simple differentiation on this function, okay, minus 2t and then plus 2.5 to confirm that the derivative is correct. Okay, now we have, this is quite a good question actually, part 2. Tick one of the following statements which correctly represents s dash of 2. S dash of 2 is the instantaneous speed at t is 2, the instantaneous velocity at t is 2, the instantaneous displacement at t is 2, or the instantaneous rate of change in velocity at t is 2. Okay, so I'll tell you, like with a multiple choice, it's always good to try and get rid of the ones that it's definitely not. So, rate of change of velocity, if we look at the bottom one, rate of change of velocity, that's acceleration, isn't it? It's the slope of velocity, rate of change of velocity, that's acceleration. That's not what we've calculated here. We've calculated the slope of displacement, all right? And so that means it's not the instantaneous displacement either. That's just the s of t function. So it's going to be one of these two. Now, speed is modulus of velocity, which means speed doesn't have direction, whereas velocity does have direction. And if we look at our calculation here, it has a direction. It has a negative direction, right? And so s dash of 2 is going to be the second box, the instantaneous velocity after t equals 2 seconds. All right, show that the velocity of the basketball is always decreasing between t is 0 and t is 3. So the velocity function that we have is minus 2t plus 2.5. Okay, if we find the root of, what we'll do, we'll differentiate it to get the rate of change function. We'll find a of t. All right. Now, what this shows you, okay, the a of t function is the rate of change of the velocity function, right? The a of t function is a horizontal line of y equals minus 2. So that means the acceleration is always negative, so the rate of change of velocity is always negative. All right? Makes sense in the context of the problem as well. You throw a basketball up in the air, immediately it stops. It starts slowing down, and then it decelerates towards the ground, right? So it has negative velocity. Show that velocity is always decreasing. So this is perfectly acceptable way to communicate that. Only one mark. If you wanted to write a comment, you could say acceleration is the rate of change of velocity. Acceleration is always negative. All right. Consider the function f of x equals x times x plus 1. Show that f dash of x is this. So, I'm going to expand the top straight away. X squared plus x on x take 1. Okay, so to differentiate this, we're going to use the quotient rule. u dash u dash. And then it's just a matter of expanding the numerator. 2x squared take x squared simplifies to x squared, minus 2x plus x take x simplifies to minus 2x, take 1, 1x take 1 squared. Okay, hence find the exact x coordinate of the local minimum. So if this is the function, this is the first derivative. Now, stationary points, a local minimum occurs when the first derivative equals 0. So we're going to find the exact value when this function equals 0. And we're going to do so, because it's a rational function, it's going to equal 0 when the numerator is 0. We don't need to worry about the denominator, we're only focusing on, you can even think about it, multiply both sides by the denominator, and you're left with that part. So we're trying to solve this. It doesn't factorise neatly, so we have to use quadratic formula. So, minus 2. Really drawing out what's going on here. Okay, so if we process quadratic formula, just a few things to point out. So we're here, we process it, we get 4 plus 4 is 8. And then if I'm trying to break it down, not that you have to list all of these operations, your calculator will do this for you. Okay, it will simplify surds to their most simple form. So if you type that in, it will spit this out. But what's going on there, root 4 times 2 is the same as root 8. And then we can pull the root 4 out front, and root 4 simplifies to 2. And then I can divide both terms by 2. So I get the 1 plus or minus root 2. Now the reason I'm rejecting the negative 1, now root 2, it's about 1.7, 1.4, sorry, root 3 is 1.7, 1.4. Now root 2, the reason I'm rejecting that is because it's a negative value, and we're told the function exists for values larger than 1, okay? So this value is obviously larger than 1, right? 1 plus something is larger than 1, but 1 take away something, it's outside the domain, so we reject that solution. Not that that needs to be listed here. Okay, consider the family of functions, x times x plus k, on top of x take 1. The table of values below shows the x coordinates of the local minimum of the function. The x coordinate of the local minimum, x on x plus 2 is given. Complete the table below for k is 1, 4 and 6. So we found it for 1. Alright, so we have x times x plus 1, we have x times x plus 2. So pull your calculators out, start sketching those other functions. I'll bring them up to you as well. We saw for this function it's 1 plus root 2. We have for this function 1 plus root 3. Okay, already a pattern starting to occur. So we'll go to x times x plus 4. On top of x take 1. The minimum, the local minimum, 3.23. That's tricky. What is that number? That doesn't match our pattern here. And so that's probably the only issue I'd take with this exam is...
Are you supposed to find the local minimum of the derivative function?
No. No, you're finding, this is the original function, you're finding when the derivative function equals 0, which is the local minimum on the original function. Yeah. Yeah. So if you want, you can do it for the derivative function, like graph it, but it'll be a root, not the minimum on the derivative. Okay, so what we're looking for is we're trying to identify what's the value there and what's actually going on, and this is something we can check. This is going to be 1 plus root 5, okay? That simplifies to that x value there, which is 3.236. And so, yeah, so it's not real clear, like if you're just g solving that one, and if you're g solving that one, it's not real clear what those values are. And this one, 1 plus root 7. So hopefully we can start to recognise a pattern there, all right? So, when we have k is 1, okay, we have 2, when we have k is 2, we have 3, when we have k is 4, we have 5. So what seems to be going on then is that the x coordinate is 1 plus, and then it's the square root of whatever the number is plus 1. Whatever that number is, plus an extra 1. That number, plus an extra 1. That number, plus an extra 1. So it is a bit tricky to see. However, this is a really good example of a conjecture that's quite tricky to see, but is very easy to prove. Okay? So if you want to charge ahead, go have a crack at proving it now. That's what we're on to. So we've made the conjecture. Now prove or disprove your conjecture. So we're talking about the function x times x plus k on top of x take 1. And we want to know what's the x coordinate of the stationary point. All right, so we're basically repeating what we did in part B. We're repeating what we did in part B, except for this function. All right, so it's ever so slightly different. So what I'm going to do is expand at the top again. So this is the function. It becomes x squared plus kx on top of x take 1. And then we'll use the quotient rule. All right, so I'll just process what have we done there. We've taken the general function, okay, and we're almost always doing this with conjecture questions, right? So this is a stationary point one, and we know stationary points occur when the slope is 0. So we're finding the slope function, all right? And so that's what we've done here. We've done the quotient rule, u dash v, uv dash, expand the numerator, collecting like terms, right? 2x squared take x squared, that simplifies. Kx and kx, they cancel, and so this is what we're left with. Okay, so stationary points occur when the derivative equals 0. Again, it's a rational function, so we're only focusing on the numerator. This is almost the same as what we've done in part B. We've just got this part to solve, and we're going to use the exact same process. We're going to apply quadratic formula. So we'll go x is minus b plus or minus the square root of b squared, take 4ac, where the c value corresponds with negative k, all on top of 2 lots of a. Now, like our first principles, by the way, and I'm going to try get in the habit of doing this, if you want to save a bit of space with your quadratic formula, you can pull that b sort of out front, like on top of 2a, you can make that on top of 2a, right out the front, and then just have our whole expression here, which is going to be 2 plus or minus the square root of, we're going to have 4, and then plus 4k. All right, so we're getting close to our conjecture here. That's our conjecture. All right, so this 4 plus 4k, the operation they're looking for there is that the number 4 is common to both of these. So we're going to factorize 4 there. Just leaving that half out front. Then we'll split the surd. We have square root of 4 times square root of 1 plus k, and we know that the square root of 4 is 2. Just put that as the square root. And there it is. You can reject the negative solution. Okay, so even though this is a very tricky conjecture to see, you don't need to see the conjecture in order to prove it. And then you can even go back and answer what your conjecture is. So again, just to recap, what do? We found the derivative, we make the derivative equal to 0, and we've solved through for the x values of that stationary point. Very good. Okay, any questions?
Can we say it racing?
Yeah, go for it. Yeah. I'll keep moving. We've got a couple here. Question 5. So we have a large number of chip-alicious cookies have been examined, and the number of chocolate chips in each cookie has been counted. The distribution of the number of chocolate chips in a chip-alicious cookie is shown in the table below. So we've got 17 chocolate chips all the way through to 22 chocolate chips. All right, show that k equals 0.1. So for a valid probability distribution, all probabilities must add to 1. So I'm going to write out all of the probabilities and demonstrate that k adds up to 1. Okay, so we've got 3k plus, and that's going to be 0.45, 0.45 plus 0.25. 3k equals 0.3, k equals 0.1. So nice generous mark there. Find e of x, I'd be going straight to your calculator rather than multiplying each and putting it in stat mode in the list. There's quite a few calculations to perform there. So we have 17, 18, 19, 20, 21, 22. And then respective probabilities, 0.1, 0.15, 0.15, 0.2, 0.15, 0.25. Now make sure you've got all of those right. 0.1, 0.15, 0.15, 0.2, 0.15, 0.25. Excellent. So E of x is 19.9. So that's part E part 2, E part 1. Alright, so we have a calculation and then we interpret. Interpret your answer in the context of the number of chocolate chips. So in a randomly selected cookie, or on average, each cookie contains 19.9 chocolate chips. Very good. Okay, find the probability that a chipalicious cookie contains 20 or more chocolate chips. So just going to our distribution above, it's the event 20 plus event 21 plus event 22. So it's the probability, these probabilities added together. So we've got 0.4, 0.6. So for part C, our answer is, so if you want to communicate it, we've got the distribution x, probability of distribution x being larger than or equal to 20 is 0.6. So that's one way we can answer it. It'd be correct just to write 0.6. Okay, all right, so we're introducing a new variable. Let y represent the number of chipalicious cookies that contain 20 or more. Give a reason why y can be modeled by a binomial distribution. Okay, so for a binomial distribution, we have two outcomes. All right, so there's two outcomes, either has 20 or more, or more or doesn't. So there's that dichotomy. It's either one or the other. There's two outcomes. There's only two outcomes. And the other property is that we have the probabilities remain the same. So like removing a large number of chipalicious cookies. So removing a cookie doesn't change the probability. But we're only required to state one. I would go for that one. Two outcomes. Okay, the manager of the company randomly selects 30 individual chipalicious cookies from the production line. Calculate the probability that exactly 15 contain 20 or more chocolate chips. Okay, so the probability of it containing 20 or more chocolate chips is this. We want to know what's the probability that exactly 15 cookies out of 30 have 20 or more chocolate chips. So this is a BPD calculation. 15 successes out of 30 trials, and the probability of a success is 0.6. That's the best way to think of it. You can think of the binomial distribution formula if you prefer. So BPD, because it's an exact event, they're saying exactly 15 out of 30, and the probability of success 0.6. So this is quite low, 0.07831. 0.0783. All right, part 2, so E part 2, a majority, so it says more than half. All right, so if we've got 30 cookies, half of 30 is 15, and so we need more than 15, so we're talking about 16 and above. So that was E part 1, here's E part 2. We're doing B, C, D, 16 and above. So between 16 and 30 out of 30, and the probability of it containing 20 or more chocolate chips is 0.6. So B, C, D, 16 to 30 out of 30, 0.6. 82%, so 0.8246. 0.825.
Do we have to write the BPD and then the stuff in the brackets every time?
No, you don't. You get full marks for the answer. Now, I would encourage you to, just because it's useful for you for backtracking when you're checking your work. Like I do it, I encourage you to do it. It communicates what you're thinking to the marker. And very rarely, like you might have the correct syntax, but then the wrong answer here for some reason. Maybe you pressed the wrong button. And so there's still potential to, not always, but there's potential to get marks from what you wanted to put into your calculator. Yeah, it's not necessary, but do it. Okay, so the managers of the company would like to claim that 90% of all Chipalicious cookies contain 20 or more. So we saw here, when we sampled 30 cookies, only 82% did. What is the minimum number of Chipalicious cookies that should be sampled for the managers to have a greater than 90% chance that the majority of cookies will contain 20 or more chocolate chips? All right, this is quite tricky. So, tricky 3 marks, going to be a trial and error question. And so we're changing, rather than having 30, we're changing this to n, all right? And so then this number is half of n plus 1, isn't it? Half of n plus 1, because it's half of it, and then 1 larger to show that it's a majority. So we have n, and 0.6, that remains the same, and then here what we have is n on 2 plus 1. And so let's set up a bit of a table here, and we'll just go n and then p for probability. And what we saw, was when n was 30, the probability was 0.825. So we've probably got to go in the lower direction. Okay, so let's go to, for example, 20. Let's set n to be 20. So half of 20 will be 10. So 10 plus 1 is 11. All right, so I'm going BCD 11 to 20 when n is 20. Out of 20, and the probability is 0.7, 0.6. No, that's probability going in the wrong direction. Sorry, that's 0.755. Okay, what about the other direction? 21. So let's go 40, 21. So for 40, I'm going from 21 to 40 out of 40. 0.6. Oh, that takes us closer. That's 0.87. All right, so let's go on 45. Now half of 45 is 22.5. So the next integer value is 23. So let's explain that. If I'm testing 45, half of 45 is 22.5, and so the integer value larger than 22.5 is 23. So I'm going from 23 to 45, out of 45.6. So that's how I'm testing for 45 circumstance. And that's 0.91. So we're very close. We should just check the circumstances below it because we want the minimum number. Okay, so if we go 44, 44 would be 23. And that's 0.88. Therefore, n equals 45 cookies. All right, so the mathematics isn't hard at all, right? The comprehension, understanding exactly how to do that. So I think the hint is they're asking you, what's the hint? They're asking you how many do we sample, all right? So we're changing n and we want the majority, so that's why we get that half of n plus a bit more. We know that probability is staying the same, and we're just changing the numbers until this number just exceeds 90%. Very good. All right. So we're on to booklet 2, and we've got an integration question. So I'll have a sketch. Another big integration question. Yep. Is everyone going okay? Any more questions? Or
So 48 is 0.896.
Yeah, so
Is that
I think
because
it goes,
45 is because it's an odd
If
number,
you plus
then the half of
0.5.
it is half.
You added
You're not adding a
0.5,
full
not
one.
one. That's why.
so
For
yes,
an even number, you can add a full one integer.
yes.
For an odd number, you add half,
Half, yeah.
and it's more accurate. Like,
Well, you can still sample an odd number of cookies, but
Yeah.
so it's not always going to be half plus one. What it should be is it's half to the next integer.
Yeah.
Yeah. Sorry, I don't know how that's
Plus
possible.
one rounded.
Yeah, half plus one rounded down. Yeah. Rounded to the next integer, the lowest integer. Yeah. All right. Let's do this integration one. So we have here a curve that looks like this, and then we have a line that looks like this. And the line is g of x, and the curve is f of x. And we have 5, and we have 7 areas. And we have point A, point B, and that's point C. Very good. Okay, calculate the integral from a to b of f of x, take g of x. So the answer to part A is going to be 5. It's the area between f of x and g of x. We don't need units squared because it doesn't ask for area, it just asks for a definite integral. Okay, calculate the integral from, now we're asked here, from c to b of f of x, take g of x. Now there's a little trick going on here because they've asked it backwards, right? They've asked from c to b rather than from b to c. So the good way to think of that is c to b, that's the same as the integral from b to c of the negative of this. So I'll do it slowly and then perform the distribution, which becomes integral from b to c of g of x take f of x. All right, so this is asking for what's the area between b and c of the top function take the bottom function, right? G of x take f of x. And so this one simplifies to 7. Again, it's not area, it's a definite integral. But that's a little bit tricky because they've got those around the opposite way. Okay, hence find the integral from a to c of f of x take g of x. Okay, so I would break this down, right? So we know that the integral from a to b of f of x take g of x, we know that that part is 5. And then we know that the integral from b to c of f of x take g of x is going to be -7. And the reason it's -7, here we did g of x take f of x, so the negative of that is the -7. 5 take 7 minus 2. All right. It is known that the integral from a to b of f of x, so the total area under the curve of f of x from a to b is 9. Calculate the integral from a to b of g of x, that has to be 4. 5 plus 4 is 9. So our answer to part D, 4 units. Sorry, yeah, should I go over it a bit more?
Yes, please.
Yep, all right. So, part C or part D? D, excellent. Okay, so it's known that the integral from a to b of f of x, just a to b of f of x, so the area under f of x, that has a total area of 9. Now we know that this part is 5, so 5 plus this component has to add to 9, so this component has to be 4. 5 plus 4 is 9. Yep. Now please ask clarifying questions. You know, the hardest part about teaching is it makes sense in my head. So I don't know if it makes sense in your head though, you have to tell me. Okay, so let's flip the page. On to question 7. Alright, beautiful. Now this question is actually quite similar to the one we went over in the exam the other day. So let's do it. We have y equals x squared ln x. Find dy on dx. Okay, so we have to use the product rule here. U dash, v dash. u dash b plus ub dash. Alright, so yeah, x squared times 1 on x simplifies to x. Alright, hence show that the integral of x ln x is this. Okay, so anytime we do a differentiation and then there's a hence, it means using this, using what you've just done. So we know from part 1 that the integral of 2x ln x plus x, we know that that simplifies to x squared ln x. And we are interested in this part of it. So we're going to break it down. Okay, we're trying to isolate that component. So the first thing we'll do is split the integral. So it's 2x ln x. Alright, now I'm going to pull the 2 out front and move that term over. I'll move the 2 over now. X ln x is half x squared ln x. Take half, perform the integral, and then plus c. And that's what they're trying to get us to show. Half times half is 4. Alright, so these ones, I want you to make sure this is a very common exam question where you differentiate and then you make an integral statement. Okay, look out for that, look out for hence, okay? You've differentiated, here it is, and even though most of the time they show you what the derivative is, they'll say show that the derivative is this, and then they'll say hence show that the integral is this. Alright, so we've done the derivative, there it is. Integral statement, we know if we integrate this, this is what we obtain. We're trying to localize it to just be this part of the integral, so we're applying properties of definite integrals. We're splitting the integral, pulling the 2 out the front, we're just isolating that component, solving through. Okay, so I want you to make sure you get those ones. Alright, the graph is shown below. An estimate for the area is required between 2 and 6. We've done vertical rectangles. Calculate the overestimate to 3 decimal places. Okay, so the function is x ln x. Okay, the function is x ln x. And we want to know what's the y value when x is 4, what's the y value when x is 6. They're going to be the heights of the rectangles. Right? Let me do a sketch so we can see it. So it goes like this. And we've got a rectangle here, and we've got a rectangle here. So we have 2, 3, 4, 5, 6. So we want f of 6, and we want f of 4 to be the heights of the rectangle. Alright, so f of 4 then is just going to be 4 ln 4, and f of 6 is 6 ln 6. All we're doing is taking the x value and putting it into the function there. So then for the area of each rectangle, well, it's the width multiplied by its height. So for the first one, it's 2 times 4 ln 4, plus, and then for the next one, 2 times 6 ln 6. And anyway, they want this to 3 decimal places. So what have we got? 8 ln 4 plus 12 ln 6. 32.5914. Now, 3 decimal places means 3 numbers after the decimal place. So it won't always be 3 significant figures. This is where they tend to pick on rounding. 2 marks there, make sure you get it. Alright, new overestimate can be drawn with 4 rectangles. So draw the rectangles for the overestimate. So using 4 rectangles, so there's our first one, that's our second one, here's going to be our third one, that's our third one, and that's our fourth one. So for the new overestimate, calculate it. So I know that the width is 2, and then the width now is 1. The width of each rectangle is 1, and then I'm just adding the heights together, which is going to be 3 ln 3 plus 4 ln 4 plus 5 ln 5 plus 6 ln 6. Alright, so the first rectangle has a height of, has an x value of 3, and so the y value is 3 ln 3. The next one, height, x value 4, 4 ln 4, 5 ln 5, 6 ln 6, and the width of all of them is 1. So the area is 1 times 3 ln 3 plus 1 times 4 ln 4 plus 1 times 5 ln 5, etc. Now calculate that to 3 decimal places as well. So we have 3 ln 3 plus 4 ln 4 plus 5 ln 5 plus 6 ln 6. 27.638. 27.639. Okay, so this one we do have to round up a little bit. Alright, with reference to A part 2, find the exact area between 2 and 6. Alright, so we want to know what's the area between 2 and 6 of x ln x. Now, it tells you with reference to A part 2, so that means using the formula provided in A part 2, using this, we know what x ln x integrates to. We're told it. Alright, this goes to, so we'll go straight to the definite integral. Half x squared ln x, take a quarter x squared from 2 to 6. And then we're just applying the fundamental theorem of calculus. So that's going to be, half of 6 squared ln 6, a quarter of 6 squared. And you can use your calculator here to like simplify some of these smaller parts if you want to. So 6 squared is 36, half of 36 is, we have 18. And then we'll 36 and a quarter of 36 is 9. What do we have? Half times 4 is 2, so we have to take away. I might distribute the negative at the same time, take away 2 ln 2. And then we're going to have plus a quarter of, is that a quarter? Yep. A quarter of 4 is 1, so it's going to be plus 1. Alright. So our answer is 18 ln 6, take 2 ln 2, take 8. We can't collect those logarithms unless we bring the powers out the front, up the top, and make it ln of A take ln of B. How we've expressed it is a perfectly suitable way of expressing it. Alright, everyone okay with that? Yeah. Alright, so what do we do there? Definite integral using the formula provided to us. Very good. An underestimate of the area in part C is to be calculated to be U. Without doing any further calculations, state with reason whether U will be closer to the approximate area compared to the overestimate found in B part 2. Alright, so an underestimate using 4 rectangles compared to an overestimate using 4 rectangles. So, what we should consider and what it should tell us is that there are no points of inflection, and we can see that the function is concave up. Now, the way we can observe that ourselves is that the slope is getting steeper and steeper and steeper. It doesn't taper off, which means there's no points of inflection. This means the function is concave up, okay? So this popped up a fair bit, even popped up in our wine glass folios where we talk about why one estimate is going to be better than another. And so because the function is concave up, I'm going to exaggerate it, this is the kind of shape that it has. And so this is the best way to communicate it. And so if we do an overestimate, this is how much error we have. This is what we call the error with over. And this is going to be the error with the under. So we're going to say because f of x is concave up, underestimate is closer. As there's less error. Alright, so we've seen that a fair bit. I won't dwell on that for too long. Alright, how many do we've got half an hour. Looking it down. Question 8. The social media platform Snapchat is used by adolescents around the world to make videos. It is known that T, the time spent on Snapchat per day, varies according to the distribution, with a mean of 1.1 and a standard deviation of 0.8. Let T of n represent the average time spent per day on Snapchat for a random sample of n adolescents. The distributions of T of 5 and T of 30 are shown below the histograms. Which histogram best represents T of 30? Give reason for your answer. Okay, so we know the larger n, the more bell-shaped, and the smaller spread of distribution. So the answer to part A is going to be histogram B is T30. Give reason. More bell-shaped, okay, so it has less skew, and the data is more centralized. That's the central limit theorem. But we can just say more bell-shaped. So part A, histogram B, more bell-shaped, less skew, less spread, all right? As n increases, spread decreases. Okay, for the distribution of T50, will the standard deviation of T50 be less than or greater than the standard deviation of T30? So this is asking about the central limit theorem, okay? Now, as n increases, this is a diagram straight out of our notes book, straight out of your textbook probably. As n increases, the spread decreases. And that's observable in these histograms here. As n increases, the spread decreases. What is standard deviation? It's a measure of spread. So as spread decreases, it means the standard deviation decreases. So will, for the distribution of T50, will sigma T50 be less than or greater than? It's going to be less, so our answer part B, less because as n increases, spread decreases. And this is according to central limit theorem. CLT, central limit theorem. Okay. Write down the mean and standard deviation of T25. So the mean of T25 is equal to the mean of T, all right, which is 1.1. And the standard deviation of T25 is equal to the standard deviation of T divided by the square root of 25, which is 0.8 on 5. Okay, hence perform this calculation. So this is an NCD calculation. So part C, part 2. Is being less than 1. So we'll go from minus infinity to 1. The standard deviation is 0.8, lower boundary, upper boundary, standard deviation, and the mean. That's what we're typing in. So minus infinity. Now, although negative infinity hours spent on Snapchat doesn't make sense in the context of the problem, it's how we model standard normal distribution correctly. So upper boundary 1, 0.8 on 5, and 1.1. So 0.263 266. Alright, everyone okay? Okay, in a class of 25 students, calculate the probability that the total time spent per day on Snapchat is greater than 30 hours. Okay, so the variable T is each individual student. So now we're looking at the collective of it all added up together. So we're asking you about the probability of variable S25, which is the sum of 25 observations, and we want that to be larger than 30. So it's the probability of S25 being larger than 30. So this is going to be another NCD calculation. The lower boundary 30, the upper boundary is infinity. The standard deviation is different from the one we've calculated here, because the standard deviation for Sn is square root of n times the standard deviation. So that's going to be the square root of 25 times 0.8. And then the mean of Sn is the mean of x times n, isn't it? So that's going to be 1.1 times 25. So that's the MCD calculation we're performing for the variable S25. Okay, normal. So from 30 upwards, we have 0.8 times 5 and 1.1 times 25. So all the same. 0.265. Ooh. 0.2659. Interesting. Now I might reflect on this question a bit later. Might be there's a simple connection between the two. But for now we've answered it correctly. We've just stated the probability. Alright, in 2023 the local government is concerned that adolescents are spending too much time on social media. The local government claims that the local daily average time spent on Snapchat has increased. The local government conducts a survey of 200 students. The sample mean was calculated to be 1.25. Assuming that standard deviation was 0.8, calculate a new 95% confidence interval. Okay, so just straighten your calculator, stats. We're doing an interval Z first sample. So our confidence level is 95%. Our standard deviation is 0.8. The observed mean was 1.25. And the standard deviation, the N was 200. So we're just typing all of that information in there. Everyone remember how to do that? And we get between 1.14 and 1.36. Now remember, for confidence intervals, they're 2 marks. You get 1 mark for the boundaries and the other mark for correct notation. Do not put X bar in there, do not put P. We're talking about the mean usage of a social media platform, and we have less than or equal to because we're including those boundaries. All right, calculate 95% confidence interval. Does the confidence interval support the claim? So they claim that it has increased, didn't they? The local government is concerned, the local government claims that the daily average has increased. Historically, the mean was 1.1, and now it's 1.14. So based on the confidence interval, the lower boundary is above 1.1. So let's answer the question. Does the confidence interval support their claim? Yes. Okay. Yes, the claim is supported. Not proven. Okay, not guaranteed. But yes, the claim is supported. So always answer the question. Marked exams, seen too many kids not answer the question, they just waffle rubbish. Get a mark for answering the question and then a mark for justifying. Yes, the claim is justified, or the claim is supported, we should say, sorry. The claim is supported. And the reason is the old, or the previous mean lies completely below the confidence interval. Previous mean lies completely below the new confidence interval. So it suggests something has changed. Okay. All right, question 9. The continuous probability density function for a randomly selected phone call lasting a few minutes is represented by this function. The graph is shown below. Show that it's a valid probability density function. So we want to show that the interval from 0 to 10 of this function. Now I'm going to start by pulling some stuff out the front and so forth. So we have cos times, and I'm going to distribute this as well, pi on 10t, take, and that's going to be pi on 2 with regards to dt. We're going to show that when we evaluate this, it simplifies to 1. That's what we're required to do here. So I've performed that distribution in there, I've pulled that number out the front. Okay, so when we integrate cos of ax plus b, it goes to 1 on a sine of ax plus b. Alright, so what's going to happen here? The pi on 20 can stay out the front for now, and it's going to become 1 on pi on 20, pi on 10, 1 on a sine of pi on 10, take pi on 2, from 0 to 10. Now 1 on pi on 10 is going to simplify to 10 on pi. And we have pi on 20. Now, I'm going to apply the fundamental theorem of calculus now as well. We're going to have sine of pi on 10 times 10, take pi on 2, take away, and then that's 10 on pi, sine of pi on, sine of pi on 10 times 0, take pi on 2. And then the square bracket. Okay, so a little bit to simplify here. 10 on pi is just hanging out the front. Now, sine of pi on 10 times 10, that simplifies to sine of pi. Take pi on 2. And then over here, we have 10 on pi. Sine of, now that's 0, negative pi on 2. Okay, then we can get into our unit circle. Now, pi, take away pi on 2, even that one, that's going to simplify. If we have pi, so at 180 degrees, take away 90, that simplifies to sine of pi on 2, that part there. Alright, so sine of pi on 2 is 1. Okay, so that whole thing simplifies to 1. So what we have pi on 20 multiplied by 10 on pi times 1, take away, and then we have 10 on pi times sine of negative pi on 2, use your calculator, that simplifies to minus 1, close that bracket, and so we have pi on 20 times 10 on pi plus 10 on pi, so pi on 20 times 20 on pi, 1, QED. Alright, so any parts there anyone wants to ask about? Alright, find the integral from 1.2 to 3.6 of the function. So, I'm just going to type it into my calculator. Option calc integral of pi on 20 times cos of pi on 10 times x times 5 from 1.2 to 3.6, and we've got 0.25. Okay, so all I've done is type that definite integral into my calculator for B part 1, 0.2519. People still on the previous part, you want a break for a sec? All right, interpret the answer. So it's a probability density function, and so we've calculated the probability of the event occurring between 1.2 and 3.6. What's the context in which it's asked? It's talking about phone calls, isn't it? Phone call lasting 10 minutes. So the probability of a phone call lasting between 1.2 and 3.6 minutes is 0.252. So we interpret it. State the average length of a randomly selected phone call. So this means, what's the mean of the probability density function? So for a probability density function, the mean is the integral from a to b of x f of x. Okay? So that's all I'm going to do straight in my calculator. The mean from, now it's valid, from 0 to 10. So we're doing from 0 to 10. And then I'm just going to put another x in there up front. The mean is 5. And you can see that in the diagram. It's very bell-shaped, isn't it? Okay. So for part 1, the average length, the mean is 5 minutes. Okay, C part 2. Find the standard deviation. Ugh, what's that going to do? Just some number crunching there. So this is chapter 8, B.
We've got it here.
Yeah. Have a read for me. I've got it here too. So there's two formulas. We'll just do this one. It's integral from A to B. So I'll just write out the formula. X squared f of x. Take the mean square root. Okay, so there's two formulas. That's the one we'll use. So I'm going to type in my calculator then, the integral from 0 to 10 of x squared times the function. I'm going to subtract the mean squared. So the mean is 5, so I'm going to subtract 25, and then I'm going to square root the whole thing. Now, definitely, this is something I would write out what you've put in your calculator for. So that's all right. X squared, value like that. Take 25, square root, and I've got 2.176. So we've done the standard deviation and the mean. Okay. The graph in figure 7 below shows a different continuous probability density function defined between 0 and 10. Let this function be g of t. Which function has the largest standard deviation? Okay. F of t, g of t will be the same. Now, standard deviation is a measure of spread. Which one's more spread? Figure 7, like the data occurs everywhere over the whole thing. It's going to have a very large standard deviation. So, for D, we're going to answer that, we tick the box, G of t has a larger standard deviation, and the justification is standard deviation is a measure of spread. F of t is more concentrated. I can write this. Okay, justify your answer, so D part 2. Sigma is a measure of spread. And we have F of t is normalish or bell-shaped, is normal, it's concentrated about the mean, which means it's not spread out, right? The results gather around the mean. And then G of t is all spread out. The results are not concentrated. Okay, so anything like that is appropriate. All right. Do we have time for one more? How do you guys feel? Do you want to stop? Or do we get it done? Get it done? Alright. So, let's do it. So, find t dash of x. There's lots of differentiation in this, isn't it? So, we're going to be using the quotient rule. Alright, so u is the top part. V is the bottom. Smash them together. All on top of v squared. Alright, so it doesn't say to simplify, but this is, yeah, e to the x plus e to the negative x squared, and this is e to the x take e to the negative x squared. So, let's do it. Okay, so just what's going on in my mind there, I'm recognising this is a plus b times a plus b is perfect squared. So I've got a squared plus 2ab plus b squared, and the same here, a take b times a take b, that's a squared take 2ab plus b squared. And I've just pulled the denominator out the front because I'm not really manipulating the denominator, I'm just going to try and see what can cancel along here. Now what we have is, we have, yeah, e to the 2x, take e to the 2x, and we have e to the negative 2x, take e to the negative 2x, so that's cancelling. These terms here are both going to simplify and then collect. So look at this, 2e to the x times e to the negative x, same base, so we can add the powers, and x plus negative x simplifies to 0, and e to the 0 is 1. So that term simplifies to 2, take away negative 2, so it collects to 4. Alright, so that's it there, that's this first derivative. Alright, show that it's increasing for all values of x. So t of x increasing for all x. If t dash of x is always positive. Alright, that means it always has positive slope, it's always increasing. Now if we look at t dash of x, that's this function here, u to the x. Alright. As x approaches infinity, now I also think we do have a restriction, no restrictions on x. As x approaches infinity, okay, what's going to happen to, remember we break it down into each part. E to the x approaches infinity, okay, so this part's getting really large, really positive, really large, and this part is getting really small. Okay, and the reason that's the case is because it's 1 on top of e to the x. That gets large, 1 divided by a large number approaches 0. So we have this part's approaching infinity, this part's approaching 0. So therefore, together, this part approaches infinity. I'm breaking it down into lots of parts here, more than it needs to be. Therefore, this part approaches infinity. And so t dash of x is 4 on top of infinity, approaching 0 from the positive direction. So what's going on there? All right, what we've done, we've spoken about like what's going on with e to the x, what's going on with e to the negative x, that part's going to 0. So this whole bottom is just going to infinity. Infinity squared is infinity. So I have 4 divided by infinity. It's approaching 0, but it's positive. It's never negative. It doesn't have roots. And we'll observe the same in the opposite direction. All right. The graph is shown below. Complete the table. So it wants us to find t of 11 and t of 13. So that's just a matter of putting those in the calculator. I'll skip ahead. You can just g-solve those or type in the number 11 into the original function. As x gets very small or very large, what value will t dash of x approach? Well, we've shown that it approaches 0. Which one statement is true? Tick the appropriate box to indicate your answer. Okay, so it's not the first box because that says t of x is positive. All right, we can see t of x is negative for values less than 0. Now, it's approaching an asymptote. All right. So, it's not, let's talk about what each of those means. So it's looking like this. All right, so because the slope is approaching 0, it means it's approaching an asymptote, which means it's not going to equal that point, but it's going to get very close to it. Okay, so it's getting very close to 1 and very close to -1. So it's not going to equal it, so we can disregard the equals 1. It's going to be the third box. It's not the fourth box because the fourth box says it exists outside of below 1 and above 1, below -1 and above +1. So it's going to be the third box. Okay. Now this is probably the trickiest part of it, so we'll speed run this. And then we'll get cruising. Okay. If t of x equals u, so the function was, I should have printed it outside. E to the x, take e to the negative x, on top of e to the x plus e to the negative x. This equals u, all right. And it says show that x equals this. So we're solving this equation for x. All right, now there's a number of ways you can go about this, but here's the best way that I've found. We're going to multiply both sides by this denominator. Now I'm going to move this term to the left-hand side. And I'm going to distribute the u. Okay, so we've moved that all over. Now, I'm going to write the e to the x terms next to each other. So I'm just rearranging the order a little bit. And if we look at this, e to the x is common. If I just look at these two terms, e to the x is common. And if we just look at these two terms, negative e to the x is common. Okay, so now, sorry, that's a negative x there. So now 1 take u is common to both sides.
Would that be 1 plus u in a bracket?
Yeah, thank you. I'm saying, why isn't that working out? 1 plus u, good. So now what we'll do, let's move this whole term to the right-hand side. And over here we have e to the x times 1 take u. Multiply both sides by e to the x. So we'll get e to the 2x times 1 take u. Divide both sides by 1 take u. and then ln both sides, and then get the half over. So we get that x equals half ln 1 plus u on 1 take u. Alright, so that's pretty nasty. Alright, 3 marks there. Talk about some marks are easy to get, some marks are hard. Those are hard. Regarding part E, hence find the exact value of x for which t of x equals 0.9. Well, remember t of x equals u, so all you're doing in that part is putting 0.9 where the u is. Okay, so the answer would be half ln of 1.9 on 0.1. That's the answer for part E. Okay, so well done. We're a little bit over, but yeah, good job getting through it.